Well, welcome. Thank you for braving the snowstorm, those that of you who made it. You know, sometimes when you're supposed to be busy doing other things, it's fun to set your troubles to music. You know, so I'm always happy to accept submissions of your 6004 experiences set to a popular song. And who knows, you may be honored by a future title slide for a 6004 lecture. We do have a quiz on Friday, so I've posted 3 of the 4 review videos up on the web, and I'll get to the last one this afternoon. As usual, there's old quizzes and lots of tutorial problems and stuff to work on. If you aren't planning to take the quiz Friday in section, which is where most of you will be taking it, you should be letting me know really soon now, by tomorrow for sure, that you'll need to make alternative arrangements. Otherwise, we'll assume we'll see you Friday. So when we last left our hero, we were busy working on thinking about an instruction set that we hope will be adequate for executing programs of all sorts. And we had finished with sort of 3 sort of classes of instructions. We had something where we were able to take 2 register values from RA and RB and then do some sort of operation on them. And we have a whole list of operations, in fact, the ones that you've implemented in your ALU, and we could take that result and stick it into a destination register. A very closely related class was the first operand comes from the register file, but the second operand actually is encoded as a constant in the instruction. And we can choose to have the second operand either come from the register file or come from an instruction encoded into the constant. And then the other set of instructions that we talked about were the instructions that allowed us to move memory locations to the registers and from the registers back to the memory, so load and store. And that let us do everything we needed to do, except that we were unable to change the flow of control of the program. We had just been fetching instructions sequentially from memory by incrementing the program counter by 4 and pointing to successive addresses in the main memory to fetch the next 32-bit encoded instruction. So here what we see is 2 additional instructions, the branch instructions, which allow us to make our program execution be data dependent. So we can compile things like if statements. And we'll see how to do compilation a little later in the lecture. But at assembly language level, we actually have these 2 instructions, BEQ, branch equal, and BNE, branch not equal. And what those instructions do is that they go off and they test the contents of register A. And the BEQ instruction will branch. It will change where the next instruction comes from if the contents of RA is 0. And BNE does much the same thing, except it's checking to see if the contents of the RA register are not equal to 0. And so you can, if you look at sort of the detailed operation of the instruction, you can sort of see that if the contents for the BEQ, if the contents of the register is 0, then we're going to actually, instead of incrementing the PC, we're going to put the PC to another location in memory. We've chosen in this architecture, and in fact it's a choice that's made in many architectures, to make the branch instructions use what's called PC relative addressing. So the new PC is calculated as some offset from the current PC. So rather than branching to an absolute address, that would have worked fine too, it turns out to be sort of more convenient, particularly for very, very large address spaces and somewhat limited addressability that we get out of our 16-bit constant, to instead arrange for the branches to go relative to the current instruction, relative to the branch instruction itself. You can go some number of instructions forward or some number of instructions backwards. And since almost all the branches we're doing are, branching around little pieces of code, it makes sense for this. Wherever I am, please skip forward by 8 and skip the next couple of instructions. So this is so-called PC offset addressing, and you'll get to see that. We'll explore the actual encoding a bit more in recitation. The other thing that you can do with a branch is you can remember what the address of the instruction following the branch is. Notice that the first thing we do is to increment the PC by 4. So whatever the PC was of the branch instruction, by the time we get down to the second line, it now points to the address of the instruction following the branch. And that always gets stuck into the RC register. So not only are we testing the RA register and conditionally changing the program counter, we're also remembering the address of the instruction following the branch in RC. And as we'll see next time, that'll be a very convenient way for us to execute procedure call and return. But we'll save further discussion until Thursday. But meanwhile, so we have these two branch instructions that enable us to branch conditionally to some other location nearby in memory. So you can say, well, how do I do unconditional branches? Suppose I always want a branch. Isn't it a pain to have to test RC? Well, we do have a particular register which has a constant value. That's R31. It always reads as 0. So in fact, BEQ of R31, where you specify R31 as the RA value, would always be testing to see if the contents of R31 is 0, which it always is. So this branch always happens. That sort of makes sense. So a BEQ, when you specify R31 as the RA operand, will always cause the branch to happen. So that would be an unconditional branch. Okay, so now what we can do is to look at we have sort of a little fragment of a C-like code here that sort of represents what we want to accomplish in sort of a high-level notation. And what we can do is actually write out the various assembly language statements. And this sort of shows the operation of the branch instruction here. So notice what we do is we load the value of the variable n, which is stored in memory. So we're using a load instruction to fetch the value of n from memory, and we're sticking the value into R2, and then we're testing to see if R2 is 0 or not. So that basically corresponds to this test where what we're doing is slowly decrementing n, and when it reaches 0, we're going to stop the factorial computation. So as long as the value of n isn't 0, then we want to do what's inside the loop. And then down at the bottom here, you can see a BEQ R31, which is in fact that unconditional branch I was talking about. Because that branch is always taken back to the beginning of the loop. So we have conditional test that allows us to branch around the body of the while when we're basically done with the while loop. And then at the end of the body of the while loop, we have a branch back to the beginning. So there's an example of two uses of branches, the second one of which is unconditional and always does branches. So that's sufficient now for us to have a Turing universal machine. We're able to make data-dependent decisions and change the execution of our program depending on particular data values. And now we can write programs that can loop forever and can test something. And if it's bigger than 17, do one thing. And if it's less than 17, do another. We're not just stuck executing programs sequentially. Yes, sir? I'm sorry, why it's called branching? Or? Oh, so what branching is so if you imagine the execution of the program, going just in a straightforward flow, what we want to do is to potentially change the execution of the program and do one of two different things. So in a sense, you can think of this control, which had sort of just been one after another, branching and making a choice at that point, either do this or do that. So the branch instructions are what we're doing. What we're doing is using them to set the PC to one of two different values, depending on the value of a piece of data. So in a sense, we're making a branch in the flow of control and conditionally, perhaps executing a different set of instructions.
So I see the if. What's the else?
Okay. So I'm sorry. So the else is to continue on. So the choices in a branch are, if something is true, go do this. Otherwise, just continue on execution. That makes sense?
Yes.
Okay. Other questions about branches? Okay, so that'll be the last of the instructions we'll talk about now. There's one more instruction that we'll introduce next time, which we're going to use to help us do a procedure return. But other than that, you've now seen the whole instruction set. And as you can see, so I'm going to add one more thing here, BEQ, B and E. And it's interesting to imagine that, that's all the instructions there are. And in fact, if you write your programs correctly, you can go off now and play World of Warcraft on your fancy 30-inch monitor at home. And all of that is built by executing billions of these per second, but this is not very complicated. It's a pretty simple little machine. So here's the summary of our two instruction formats, one of which has 3 registers, 2 register operands and a register destination, and one of which has a register operand, a constant operand, and a register destination. And as I say, we're going to talk about jump next time, but otherwise you've seen all of these guys. And here we go. All right, so in theory now, if I gave you a hardware interpreter for a beta, you could sit down and fill the memory full of ones and zeros to make it do whatever you wanted. Well, of course, no one in the modern world actually does the programmable part of a programmable machine by writing out strings of binary bits representing each instruction. We tend to want to use some sort of higher level language. So what we'll be doing for the rest of this lecture and next is actually talking about how these higher level languages can be translated into sequences of machine instructions to give you some idea of how compilation works. So at the lowest level, what we have is this very simple binary format. Most of us would prefer, even if writing an individual instruction, to use some sort of symbolic representation where we say, look, I want to do an add of R2 and R3 and put the result in R4 rather than writing out this magic 32-bit string. So this is what's called assembly language. And we'll talk a little bit about that in the next 10 or so slides. And then after that, we're going to think about writing in a high-level language where we don't really think much about the actual location of values, whether they're in memory or in registers. We're going to let the automatic programming system take care of that for us. And instead, we'll just label we'll label values symbolically with a name. So we'll call a particular value A and another value B and C. And we'll just refer to them by that symbolic name, and it will be up to the compiler or interpreter to figure out where in memory those values are actually living at the moment. And so we have this high-level language, and almost all of us do our programming now in the high-level language. Given the high-level language, we have several different approaches about how to execute a high-level language statement. So you could write in Python, or you could write in Java, or you could write in C. And there's 2 different basic approaches to running those programs on the machine, sitting at your desk at home. And the first is interpretation, and in some ways it's the simpler of the 2 approaches because you have some hardware that you're running, in this case, say a beta, a little hardware interpreter. It reads in those 32-bit binary numbers and executes the instructions one by one. Instead, what we'll do, and so you could say, look, I could write in an assembly language, but that seems very tedious. So what I'm going to do instead is to spend some time and write a program, which is called the interpreter, which I'm going to use as, if you will, another level of machine. So there's this notion of a Python machine, and the Python machine has Pythonic operations. You can use, tuples and lists and dictionaries and things like that. So this machine has a much more interesting repertoire than just 32-bit binary numbers. And it provides for all sorts of exotic control structures and threads and neat things like that. And then what I'll do is to I'll write in a high-level language that's meant to be executed by this really nice machine, M2, and then I'll write a program in M1's language that interprets M2 programs. And by interpret, what I mean is that it doesn't do a permanent translation from M2 to M1. What it does is that it takes a representation of the M2 program and then just sort of looks down and does each statement one at a time while the program is running. There's no permanent translation that goes on. That'll come up in the next thing. So we have this sort of notion of a hardware, an x86 or a beta hardware, on top of which we might, for instance, write a Python interpreter, and then we would write my application in Python code, and the interpreter would basically look at a representation of my application and choose to sort of walk around the representation doing whatever it says. No permanent translation, but just sort of on the fly interpret my Python code sort of statement by statement, and if there's a loop, it'll go back and start reinterpreting the statements at the top of the loop. And of course, on top of that, my application may in fact be interpreting, data or something like that. So that's sort of what interpretation is going to do. An easy way for us to write in a high-level language, but through all the hard work here of the Python interpreter, actually execute it on a machine like the x86 or the Beta. Compilation it does much the same thing, except it involves a permanent translation of the original program, a Python program or a C program or a Java program, into a separate new program. And the idea is that this translation preserves all the semantics. It figures out how to use the low-level details. If I have a list, how is that actually represented in memory? And if I access the 17th element of the list, what does that actually mean in terms of beta instructions? It figures that out all at once. At compile time, it does it once, and then when you actually run the program, there's no reference back to P2. The program is actually just a sequence of assembly language statements that the hardware interpreter runs. So this notion of this sort of one-shot translation, this program we call a compiler, does that translation once, and then the program you run is the so-called compiled program, or in this case it's usually a representation of the actual assembly language instructions, which then get executed. Okay, so why do we choose compilation versus interpretation? And it has a lot to do with just sort of what is easier at the moment. Typically, running interpreted programs involves sort of less steps. You don't have to go through a compilation step. And so you tend to you can use interpreting programs like, Ruby or Java, or Java is somewhere in between, but Ruby or Python or something like that, JavaScript. You can pound out the code and you can run instantly. So I have to go run the compiler and then take the output of the compiler and load it onto the machine. So interpreters are sort of more agile, but they often pay a bit of a performance penalty because there's this layer of interpretation that's going on, as opposed to directly translating the program into machine language statements. So here you get sort of a sense of, if I type in x plus 2 in a program, an interpreter would actually say, okay, I'm going to look at, get the value of x, and I'm going to get and add 2 to it, and it sort of every time it ran across that statement, it would do the same thing. Whereas the compiler would look at the statement and actually generate beta programs that would do a load and an add and so forth and so on. And then once that translation happened once at compile time, thereafter the machine would simply just execute the beta instructions. Okay, so we always have this choice about what we do at compile time and what we do at runtime, and we often, when we want efficiency, we want to do as much as we can at compile time, because that happens once, and then when my program runs, I don't have to redo it, whereas interpretation often gets me to execution a little bit more quickly, but the execution itself is slower. Okay. Okay, so we're going to talk about sort of our first steps is just simply taking that symbolic representation of assembly language programs and thinking about how to actually have them write something called an assembler that takes an assembly language program and produces the binary representation of the instructions in memory. That's going to be pretty straightforward. And then towards the end of lecture, we'll start talking about the process of taking a high-level language like C and translating that into assembly language, which can then be translated into the binary representation. And then on top of that, we will, later in the course, talk about different sorts of interpreters, and the one that we'll actually spend a lot of time on is the operating system. So we'll come back to that. Okay. So the first thing we have to do is to think about what does this assembly language program do? So I'm going to talk a little bit about what an assembly language program looks like and sort of walk you through very briefly the process by which that ASCII file gets translated into the binary representation of the sequence of instructions. This chicken and the egg problem is pretty interesting. If you're starting off with a raw machine, what do you write the assembler in? I mean, you can say, I want to write an assembler so I can write assembly language programs so I can run them on the machine, but the assembler is a program, and what does it run in? And thankfully what happens is typically when there's a brand new shiny piece of hardware, I go back to the machine I've been using and I actually write a cross assembler. I write something that on my old machine will read an assembly language program and translate it into binary for the new machine, and then I can assemble the assembler and run everything natively on the new machine. But how did that start? There must have been a time when there was no assembler and somebody must have keyed in the binary for the assembler, and in fact that's what happened. When I first started using machines, I won't say how long ago, the way you started a machine is you sat down at the console and actually using buttons keyed in a set of little instructions directly into memory, the binary representation of the instructions into memory, which would cause it to read the paper tape, which would then load the rest of memory, and away it would go, right? So we knew a lot more about assembly language in the old days than we seem to have to know now. Okay, so what does an assembly language program look like? Well, the simplest sort of assembly language program is just a list of numbers. And we can write them in decimal or binary or hexadecimal, whatever is convenient for us. And the assembly program just takes each one of these numbers and turns them into, in this case, 8 bits worth of memory. So this, I can take this binary representation and I can come up with an 8-bit pattern that is then put in binary pattern, which becomes the value of the next byte of memory. So this particular sequence of 1, 2, 3, 4, 5 values would represent the binary pattern that will appear, the integer representation of the binary pattern that will appear in 5 consecutive bytes of memory. Okay, now of course just constants are a little tedious, so I'm going to want to be able to write expressions instead of just simple numbers. So in fact the assembler allows you to use the standard sort of simple operators, plus, minus, times, this is logical and, so forth and so on. And of course all of these evaluate in their different ways to the actual number 23, which has a very particular binary pattern which could appear in a byte. Now, very quickly you get tired of imagining just, you can say, well, this is going to be a big help, Chris. I mean, so instead of actually keying the values into memory, I can write them out in text, and now I have a program that will translate them from a text representation of the number into the actual binary bits. And you say, well, that doesn't seem very helpful. So we're going to now do something that will get us a lot closer to writing, things like add of R2, R3, R4. So the first thing I'm going to introduce is this notion of symbols, a symbolic representation for a numeric value. We'll discover that that'll make things a lot easier. And the way the assembler works with that is it's going to build itself a symbol table. And a symbol table is just a data structure that takes the name of a symbol, for instance, X, and it associates it with a particular value, in this case hex 1000, like so. And so whenever, then when I could write an expression like x plus 1, and what the assembler will do is says, oh, the symbol x, I need to get its value. It will go to the symbol table and say, oh, he's using x currently to be the symbolic representation of this number 1000. So the assembler would know to translate this into the hex number 1001. That makes sense? So we're just, and you can sort of say, well, why bother give a symbolic name to something? And one, it will help us make the program easier to read. For example, when I'm referring to registers, I almost always use the symbolic name of the register, like R0. And I mean, at the bottom, at the end of the day, the assembler is going to want a 5-bit value to stick in that field. You could have written an integer or an expression, 3 plus 2. And you can say, aha, see, that's my clever way of talking about R5. But you'll find it be much more easy for other people to read your program if you actually wrote R5 and someone say, well, R5 is the name of a symbol which somewhere in my symbol table, okay, is associated with the actual numeric value 5. And if you look, you can see the beginnings of a bunch of statements which are actually buried inside beta.uasm, which appears at the front, is included at the front of all your assembly language programs, that set up a bunch of symbols for you to use to make your program a little easier to read and write. Okay. We'll see very quickly another use for symbols, but this is just, you can say, okay, so that sounds convenient, Chris. I'm sort of skeptical, yet I want to write an assembly language. Actually, as it turns out in Lab 5, you will have to write some assembly language programs, so this is, we're getting you started here. You can introduce comments in an assembly language program by using this vertical bar that from there to the end of the line those characters are not treated as directives to the assembler. Those are just treated as comments that are ignored by the assembler. Okay, we have a special symbol called dot. So one of the entries in the symbol table is a symbol that's spelled just with the letter period. And that represents the next location to be filled in memory by the assembler. So when you start running the assembler, dot is initially 0, and every time the assembler evaluates an expression and gets an 8-bit value and puts that value in memory, it puts it at the location pointed to by dot. So it says, okay, what's dot? Oh, 0. So this next byte I've assembled goes in location 0. And after it does that, and it increases dot by 1, and says, okay, the next byte I fill will be at address 1. So dot is just sort of this little finger the assembler is using to keep track of where it's putting stuff in memory. And so this basically says, okay, dear Mr. Assembler, please set dot to hex 100, which means I want you to start filling memory at byte hex 100. And then here's some values, 1, 2, 3, 4. And now you can sort of see, this expression here basically says, oh, the symbol 5. So we're going to add a new entry to my symbol table. So this got low, so as I put, dot was 100, and then it's 101, 102, 103. So now dot is 104, hex 104. And now that directive, which defines the value 5 to be equal to whatever the value of whatever that expression is. So on the other side of the equal sign, there's an expression. In this case, it's the single symbol dot, which has the value hex 104. Okay, and the most common thing we use symbol for is to remember a memory address so we can reference it later. Because it turns out that we're going to need a memory addresses to know where the beginnings of procedures are or where in memory a particular variable lives. And when we write an assembly language, what we're going to do is to ask the assembler, we're going to give a symbolic name to the address of that location, and from thereafter we won't deal with addresses at all. We'll simply just use that symbolic name for the address of a particular location, which holds an instruction or a piece of data. Okay, so you can see some more examples here. Now this x equals dot, you'd see a lot when we're doing assembly language programs. So in fact, we have a special abbreviation where we just use the name of the symbol colon, and you know that to mean, look, please make the value of the symbol x equal to the address of the location that I'm sort of at the current place in my assembly language program. So for example, I'm setting dot to hex 1000, so I'm expecting to fill up memory starting at hex 1000. This squares dot says, please remember the address of this location. Okay, and you can say, well, why didn't I just set it to 1000? This seems a little redundant. Well, the point is that typically you're going along and you have a whole bunch of statements which are filling up memory. You don't exactly know how much room they take, so you don't actually know precisely what the values of squares is, but you do know you want it to be the address of the location holding that 0. That makes sense? So what we're doing is just saying, look, please, Mr. Assembler, please remember where you are. Tell me, you know where you are. You've been filling up memory. Just remember, take that value, the address of where you are in memory, the value of the symbol dot, and store it away in a separate name so that I can refer to it in the future. So I can later on use the value SQRS, the symbol squares in an expression, to refer to the address of that location. Okay, so here's a bunch of expressions that fill up 16 different bytes. You can see 16 different bytes. And you can see the bytes slowly being filled in one by one. And then there's this long guy here. I'll show you about macros in a second. This is a macro call with this numeric argument. And what that's doing is actually computing the distance between where I am now and where the array started, which actually has the difference between those two values is 16. There were 16 bytes that got filled. And so that number 16 is actually encoded in 4 consecutive bytes there. Okay, so what are macros? Yes?
By frequency, S colon and then the value rather
Oh, so why didn't I write squares equals? Oh, S-len equals what?
Equals the same expression.
Right, so, oh, equals that?
Yeah.
Okay, so equals basically is something that happens at assembly time, which is to evaluate an expression. And this is actually a macro that fills up memory. Right, and so something equals a macro doesn't, the macros don't have values. Their job, they don't have a value, but their job is to actually add some more bytes to memory. Right, so we use S-len colon to basically say, please grab me the value of dot. Please get me the address of the memory locations that are about to be filled by this long macro. Yes?
So squares colon says set the variable squares to be the location you're at now?
And in fact, it will set it to be, if I actually looked in the symbol table, I would discover what the assembler has remembered for the value of the symbol squares is the number hex 1000.
So then what exactly does it mean when you have the list of numbers after?
So these are just expressions, each one of which will be evaluated, and that the result of evaluating that expression, expression 0, for example, will take that set of binary bits and put it into the next byte of memory. So this expression fills a byte, and then this expression 1 fills the next byte, and you can see that here. Here's the bytes in memory listed out. So each of these expressions, which turn out to just be numbers, has been evaluated, and since there's 16 numbers, I filled up 16 bytes of memory.
So does the numbers necessarily have anything to do with what squares is?
Squares is the address, is the symbolic name for the address where the first element of this little array is. Then I'm specifying the contents of the array element by element after that. Okay, so what are macros? Well, macros are, and they're very dumb. I'll tell you right now, they're very dumb. I define a macro, so here's the name of a macro. They take a parenthesized list of arguments, and they simply do simple text substitution. So if I write consec 37, okay, the assembler, when it says, okay, consec is a macro, so I wrote consec 37, it's going to it's going to replace this statement with the expansion. It's going to lexically substitute the characters 37 wherever n appears in the body of the macro. So the first thing the assembler does is expand that into this, expanding the body of the macro to look like so. Right? I've just substituted 37 for n lexically, and now I have these 4 expressions, each of which will be evaluated and fill up consecutive bytes of memory. So this has the same effect as for instance, that line of numbers. And you say, well, is this really going to get us somewhere, Chris? And the answer is very quickly, and so let me get there. Here's some macros, for example, for filling up a 16-bit word, 2 consecutive bytes, or a 32-bit word, which is 4 consecutive bytes. And you can see it takes the argument and sort of breaks it down using mathematical operations into its component values, into the into the bottom 8 bits, and the next 8 bits, and the third 8 bits, and the fourth 8 bits, and so forth and so on. Okay. So if I actually wrote this, what I would find in location 100 is this consecutive set of values, starting at the low end. So if you have a 32-bit number, what order it appears in memory? Do you keep the address of the low-order byte or the most significant byte? This has been a sort of an interesting tussle throughout the history of computer science. Some machines, for example, most of the machines produced by IBM or MIPS, use a big endian approach. In other words, you put the most significant byte of a long value in the lowest memory address. Other machines, like the x86 and the Beta, use a little endian approach, which puts the least significant byte at the lowest address. And it's exactly equivalent so long as a convention, so long you're consistent. That's all, by the way, taken from the name, those names came from Gulliver's Travels. 1726, Jonathan Swift wrote Gulliver's Travels. And the 2 people on this island fought over which end of the egg you should open. If you have a soft-boiled egg, you're going to eat it. Do you crack open the little end of the egg or the big end of the egg to eat it. And so they got known as little end ears and big end ears. So when people started having this fight about how to put multi-byte values into memory, which goes at the lowest address, a guy named Danny Cohen actually wrote this very nice article saying it's absolutely equivalent, it's just a convention, we just have to be consistent. So hence the little end ear and big end ear. So we're a little end ear group here, but no political statement implied. So finally what we can do is begin to write some macros that will assemble the instructions for us. So we will provide 4 different values here, an opcode, a numeric, a 6-bit opcode, and the numbers for 3 registers. And then this long, complicated arithmetic expression, its job is to fill up 4 consecutive bytes of memory with the binary representation for this instruction. Okay, so if I have this instruction down here, I'll write an addc macro that will actually expand into this macro, and then I can watch this macro slowly take each of the operations, each of the arguments, and do this arithmetic that I specify here, and it will slowly fill up the word with each of the component values by shifting and adding them together, and come up with the actual 32-bit representation for, I've started off with this, actually is what I wrote. That expanded into this macro, which expanded into this call it the long macro with this long arithmetic expression, and where I'm going to substitute these values in. So every place I see op, I'll put in 0x30 and so forth and so on. So it's a very simple little sort of language that will actually let me assemble contents for any particular type of assembly language. In this case, I've defined enough macros to allow me to write beta assembly language. But I could have written an x86 assembler or a MIPS assembler using all the same technologies. I would just change my macros a little bit. I'm not going to go through this line by line, but you can see there's all these layers of macros. The thing slowly expands. We finally get some numbers expressions to evaluate, and then some numbers, and then finally we end up with the actual binary pattern after many layers of macro expansion, the actual binary pattern that ends up in memory. We define ourselves some convenience macros. So if we want an unconditional branch to a particular location nearby, we can do that, which, we can say, look, BEQ R31 is not the most obvious implementation of an unconditional branch. So, okay, so much for assembly language. It's not very complicated. I hope you'll just sort of practice it when you get to Lab 5. You'll discover it's pretty easy to do. It's very low level. It gets a little tedious to figure out exactly the sequence of beta instructions you'll need, but the actual notation of writing them down and the translation to binary patterns, I hope, is now a little bit more clear. What about a language like C, where now I'm just talking, there's almost no references to registers or addresses or memory locations at all. What I'm doing is dealing entirely with is symbolic names for values, so-called variables, and then sequences of operations. And we prefer this because all the details of the machine are pretty much hidden away. And in fact, there are C compilers for MIPS machines and beta machines. We have a C compiler for the beta, and C compilers for the x86. So I can take one sort of machine-independent representation of the computation that I want, and the compiler, depending on which compiler I use, will translate that into the appropriate list of assembly language. So this was a sort of an attempt to build portable software. And the guys who invented C down in Belgium, so Fortran was one of the earlier examples of a machine-independent, notation for a sequence of operations on values. C was invented in the 70s to be a slightly more congenial representation, particularly for writing sort of simpler, more operating system-like code than Fortran was. Fortran was really great for formula translation. Fortran was really great for sort of scientific and engineering calculations. It was less good for writing operating systems and things like that. So that's where C got created. So let's talk a little bit about how compilation works. What does a compiler do to get the job done? And I think what you'll discover is that at least a dumb compiler is a very straightforward little engine. It's just this little, we'll write a little recursive definition of the compile function, and mostly it will call itself to compile pieces, sub-pieces of the thing I'm trying to compile. And eventually, with all those recursive calls, you get down to things like, please compile, a reference to the variable x, or please compile a number. And by compile, I mean, please do whatever you need to do and put the answer in a register. And then at the next level, we'll then use the values in the registers to do the multiply or the add. Anyway, we'll see how this works. Okay. So for example, suppose I have two memory locations holding x and y. So in C, when it sees you declare a variable, it says, oh, I'm going to need a memory location for that. So it goes off and creates assembly language programs that will actually create reserved locations in memory to hold the values of particular variables. And then when I see an expression, I sort of have to say, well, I have to do this assignment. So first I better get the value of that expression into a register, and then I can use a store instruction to store that register into y. And to get the value of this expression, I have to do a multiply. So I'd like to get the value of x minus 3 in a register, and the value of y plus 1, 2, 3, 4, 5, 6 into a register. And then I can use the multiply instruction to multiply the two registers and leave the result somewhere in another register, and then the store instruction can take that value and stick it into y. So you can sort of see this as sort of recursive descent as I'm busily simplifying the expressions. At each level, I'm saying, I better get this value and that value in a register, and once I do that, I can use the multiply instruction. To do, for instance, x minus 3, I have to get x in a register, and I could, in theory, get 3 in a register and use the sub instruction, but as it turns out, the compiler says, wait, I know how to subtract small constants from a register, so I don't need to put the value of 3 into a register. All I really have to do is to put x into a register and then use the sub-c instruction to subtract 3, the constant 3 from it. And you see all that coming out here, just like that. But I'm trying to give you a sense of how this is a very simple sort of little recursive process where mostly you ask the compiler to take some little piece of what you're trying to compile and put this value in a register, and you do that for all the pieces you need. Now you have everything you need in registers, and now you can just output the appropriate beta instructions to combine those registers. And now you've finished your expression, and your level of compilation is done. The result's in a register, and so forth and so on. Data structures like arrays. Well, an array is pretty simple. It's just a consecutive locations in main memory. So a single variable held, was one location of memory. An array of 100 values would just be 100 locations of memory. We have this notion of the name of the array actually refers to the address of the first element of the array. That's how C works. So if you say this in C and then you talk about hist, it's actually an integer pointer that points to the first location in the array, the address of the first location in the array. And then when I do index into array, I have to take this number, whatever score is, and convert it into the appropriate address. Well, each location takes 4 bytes, so I have to multiply my score value by 4 to turn it into an offset from the beginning of the array, and that gives the address of the memory location I need to access. All this is going by sort of fast, but you can look at the slide more carefully to sort of see what's going on. Data structures are much the same way. If you're into figuring out how structs work and pointers, there's some examples on this slide. How do you compile things like high-level programs, like high-level statements like if? Here's if and if else. And so these represent control structure. We're getting away from expressions, and now we're saying, look, depending on the value of expression, I either want to cause this part of the program to be executed or not. And you can see here's how the recursive invocation of the compiler goes. When C sees this, it says, please output code to compile the value of the expression into a particular register Rx. Then I'm going to, at this level of compilation, when I'm compiling the if, I'm going to follow the code that evaluated expr by a branch that tests to see whether it's 0 or not. So if it's not 0, in other words, if this expression is not true, I'm just going to branch around this code here, and then the code that I'm going to compile here is the compilation of stuff. So what we have is this little template-based approach to compilation for all the control structures. So if and while and for, those are all sort of templates that let me say, look, I need to compile up some pieces. I need to compile expression. I'll need to compile code for everything that's in the body of the if. But here's a couple little extra assembly language program statements that I'll use to control which parts get executed and which parts don't. Okay. So you look at this and say, well, this seems pretty, I can sort of see how this would work. I'm using particular instructions to test the values of expressions and then branching around code that I don't want to be executed. So that these templates, you can sort of see how the if compiles into this and then if else compiles into that. So just spend a little while thinking about what this means in C and see that this beta assembly language is accomplishing the same thing now at the level of beta instructions. Sometimes the compilers have to get a little weird. For instance, y is greater than 32. Well, you look at this and you sort of go, wait, I don't actually have a greater than instruction in my beta. I only had a compare less than and a compare equal and a compare less than or equal. I don't have a compare greater than. So sometimes the compiler actually has to reverse the sense of the comparisons and sort of do the opposite. So what it's really doing is instead of checking to see if y is greater than 32, it's checking to see if 32 is less than or equal to y and branching. So there's nothing very mysterious about that. But the compilers do have to know what the machines can do and what it can't. Okay, so now we have some loops. How do we compile? Here's a while statement. And here you sort of see we need the result of expression. If the expression is not true, we're done with the while. If the expression is true, we execute the body of the while, and then we branch back to the beginning of the loop, while loop, when we try evaluating the expression again. So, it's just this very simple little template that we use. Sometimes here's another template we can use, and this template does exactly the same thing. Okay, but this seems slightly more complicated. Why do we have this branch at the beginning? What are we doing? So what we're doing is, in fact, putting this one branch, the test at the bottom, and branching back to the beginning of the loop this way. And the reason we've chosen to do that, if I think about this loop, there's this branch instruction that gets executed to test the expression, and this branch to go back to the beginning of the loop. Here, when I'm in the body of the loop, you can see that, in general, only one branch instruction is executed for each pass through the body. You can say, this is a lot of work. It's a little weird. Why is that template actually has one fewer instructions, one fewer branch instruction for each iteration of the loop? And now you can sort of get a sense of how compilers get complicated. They're trying very hard to make sure that your program is executing as few instructions as possible so it will run as fast as possible. And nowadays, optimizing compilers are really much cleverer than you and I are, and they're able to take your high-level program and figure out all sorts of optimizations in order that you execute as few instructions as you need. It doesn't do a lot of gratuitous extra execution if it can help it. So these optimizing compilers are really quite good. And in particular, they're always concerned with loops, because every time you save something in a loop, an instruction in a loop, because loops often get executed, tens and hundreds and thousands of times, you're actually saving tens and hundreds of thousands of executions of an instruction. So these little optimizations add up to actually fairly significant performance gains. Okay, so we'll take one last little look here. Here's my little factorial program, a little iterative, it uses the while loop to compute factorial. And here's a very straightforward translation, sort of statement by statement, okay, of a particular C statement using the templates in the case of the while, or using our little expression technology for compiling expressions, R equals R times N. Well, I have to load N into R1, and I have to load R into R3, then I can multiply them together. So I've now evaluated this R times N, and I restore the result back in R, for example. Okay, if I look at this, there's 11 instructions in that loop. But if you gave it to any self-respecting C compiler, it would do a much better job. It would notice some things, improvements it could make to that assembly language code. Okay, and it's these little improvements that actually result in why we tend to use compilers even for very high performance code, because they're very good at these optimizations. So we take these 11 instructions and say, okay, well, I'm going to be doing a lot of factorial. I wish I could run my program 2 or 3 times faster. Is there something I can do? Are there ways of rewriting this assembly language to get the same effect, but to do fewer instructions? Well, the first thing we can do is to keep value, instead of getting a value from memory, manipulating it and storing it back into memory. I can just move it into the registers once and just keep the value in a register. So this register allocation, this notion of saying, can a value live in a register? So here the compiler has chosen to put the values of n and r into two registers, and now the loop just refers to the registers for the values of n and r. And when the loop is done, it takes the final values of the registers and put them back into memory, because just in case there's more things that refer to n and r down here, we have to have the correct values. But while I'm in the loop, I'm referring only to register values. So I've gotten rid of all the loads and stores. So now we're down to 5 instructions in the loop. And now we're going to do that sort of this little optimization around while, where we've managed now to only have a single branch inside the while loop, not 2 branches, a single branch. So we've gone from 11 instructions down to 3 instructions in my loop. My program is almost 4 times faster as a result of just making some observations about how to compile loops a little bit more cleverly. So that's pretty neat. It turns out that factorial, the numbers get big quickly, so it'll in fact overflow the 32-bit representation even with small arguments, but that's sort of an aside. But the thing I want you to notice is that with an optimizing compiler can actually do a pretty good job. You take a relatively dumb program where you're just saying, look, take the values of n and r, who cares where they live, and since the compiler has the choice about where they live, it can be very clever about them and actually produce programs that are actually fairly highly optimized. So we're going to stop there, and next time, the last thing we need to talk about are procedure calls, and that will take us a whole lecture to deal with. Good luck in studying for quiz 2, and remember to check off lab 3 this week, and then you'll be all set for a nice, relaxing, and hopefully snow-free spring break.